Okay, so what we're going to do today is basically finish up a little bit from last time, and then we're going to go for the Fourier inversion formula. So like recovering the function from its Fourier transform. Okay. So just to remind, so let me just put up what we had at the end of class last time. So we had some properties. So if you have a function in the Schwartz-class, and you have a constant and then a positive constant, then we had the following properties that if you take the so if you start off with this translation function and you take the Fourier transform, so take the Fourier transform, what you get is the Fourier transform of the original function, but multiplied by, but shifted, the frequencies are shifted by h, right? So this was the translation becomes modulation, right? And then we have the opposite thing, so modulation, but negative modulation of your function. If you take the Fourier transform of that, then that turns into translation. Okay. So if you modulate your function in the opposite direction, then take its Fourier transform, that turns into, and these are pretty straightforward. The third one was that if you scale your function, if you scale the time axis, then what that turns into is what's called dilation. So you get f of xc over, so 1 over delta times f hat of xc over delta. So I call this one scaling, and then this is dilation. So scaling turns into dilation, and actually the opposite is true, that dilation turns into scaling. So if you dilate the function, then it turns into scaling by the reciprocal. So also backwards. So dilation turns into scaling. Number 5 was that differentiation on the Fourier transform side turns into multiplication by the variable, and again, if you multiply by negative 2 pi ix, then that turns into differentiation. So take Fourier transform. Okay, so these are just like the basic properties of how the Fourier transform interacts with these simple actions. Okay. And the point of this for us is the fact that then you get that if f is in the Schwartz-class, then f hat is also in the Schwartz-class. And the proof of this is just to use these properties. So you say well, we want to show that the Fourier transform is in the Schwartz-class, right? That's to say that you want to show that all derivatives of f are rapidly decreasing. We're going to show that all the derivatives are rapidly decreasing. So you say, well, look, consider your function multiplied by -2, and consider your function multiplied by negative 2 pi I x to the L. Okay. And then that differentiated k times and divided by 1 over 2 pi I to the k. Okay. So first off, notice that that's still in the Schwartz-class, right? Because you're multiplying it by a polynomial and you're differentiating, right? So this is still in the Schwartz-class. Still in the Schwartz-class, and so its Fourier transform is bounded. Okay, but then when you take the Fourier transform, and I always write transform with an x for some reason. This was for some reason back when I was in college. This was common notation, like transform. Anyway, when you take the Fourier transform of this, what do you get? Well, right, the differentiation, right? Differentiation when you take the Fourier transform turns in multiplication by 2 pi I c, right? And we're dividing by the 2 pi I to the k, so we get c to the k, right? And then the multiplying by the polynomial turns into differentiation, right? So you get the Lth derivative of the Fourier transform, right? Right. So we're just using the basic properties. Okay. So what does that tell you? That tells you that this thing, this is the Fourier transform of that is bounded. Right. But that's exactly rapid decrease. That's exactly rapid decrease of the Lth derivative, right? And so you know that. So you know that you could do this for whatever L and K, and so so the Fourier transform is still in the Schwartz-class.
What does it say after the one to show all?
Want to show that all derivatives,
okay.
All derivatives of f are rapidly decreasing. Right. Okay, so this is just an application of the basic properties. Okay. Okay, let me erase this. So that's sort of closing up what we wanted to say about the Schwartz-class for the moment. What we're going to do now is go for the inversion formula. Okay, so the Fourier inversion formula that says that you can recover your function. You can recover your function by taking the Fourier transform and then it's sort of it's the analog of the recovery in the Fourier coefficient sense, right? That you can recover your function by integrating the Fourier transform against the characters. Okay. So let me just fix that for now. Okay. So okay. So the way we're going to do it is by first create. Going for the Fourier transform, going for Fourier inversion. And the first step is to create an approximation of the identity. Okay, so this will be just like the approximation of the identity that we had before. It's just that this will be on the real line and not on the circle. So we'll want the function to have the same sort of properties, right? We'll want it to be in L1, we'll want the integral. We'll want the integral of it to be to be bounded. We want the L1 integral to be L1 norm to be bounded, and we also want that third property of decay away from the origin, right? So like as you remember, so like you want three things, right? You want this thing to be finite. You want this thing also to be finite, right? And you also want that away from the origin, that the limit as n goes to infinity for you want you want the limit as n goes to infinity to be 0 for x outside of, so for any delta, right, you want your function to, outside of the delta neighborhood of the origin, you want your function to decrease uniformly to 0, right? So those were the three things that you wanted for a good kernel, and we're just going to do it on the real line now. Okay. So good kernels will mean the same thing, just now on the real line. Okay, so the thing that's going to be really useful for us is functions of this form. So we call f of x e to the negative x squared a Gaussian function. Okay. And observe that e to the negative ax squared is in the Schwartz-class for all a's bigger than 0. So it's got this very fast decay. Okay. And it's an exercise that you probably saw in Calc 3 that the integral from negative infinity to infinity of e to the negative pi x squared is actually equal to 1. So I'm not going to do it. This is like often when in Calc 3 when one introduces polar coordinates, one does this as an exercise. So you can prove it by multiplying it against itself and then getting an integral on the plane, and then switching that integral to polar integrals to a polar integral, and then it becomes easy. Okay. So what's important about this for us is the following: that if f is this particular Gaussian, then f hat equals f. Okay. So f is preserved by the Fourier transform. So one way to show it is to show that we'll show that this function satisfies a particular initial value problem. So let f of c be f hat of c. That is to say, the integral from negative infinity to infinity of e to the negative pi x squared, e to the negative 2 pi I x c dx. Excuse me. Okay, so what we're going to show is that we'll see that f prime equals negative 2 pi c f of c. Okay, and then which tells us that f must be of the form e to the constant e to the negative pi c squared. Okay, and then evaluating at 0, we have f of 0. F of 0 is going to be this e to the negative pi x squared dx, which is 1, right? Which tells us that that c is equal to 1. Okay, right. So f hat would be equal to f hat will still be equal to f. And then seeing that so what we need to show is just this that this thing satisfies this differential equation, and so we just differentiate it. Okay, so we differentiate f prime c, right? Well, that's going to pull off the constant here, right? So we get negative 2 pi x, and then same thing, e to the negative pi. E to the negative pi x squared, e to the negative 2 pi I x c dx, right? But this thing here is I times, this thing here is I times f prime, right? Because this is f. And when you differentiate it, you get the negative 2 pi x. You get the negative 2 pi x. Right? So you get I times f prime x e to the negative 2 pi I x c dx. Right? So you pull the I out, and we see that you get I times the Fourier transform of the derivative, but we had from over there that the Fourier transform of the derivative is going to be 2 pi I e times the Fourier transform of the original function, right? And so we get negative 2 pi I c f hat c, right? Which is what we wanted.
The i's cancel.
I'm sorry. There we go. Negative 2 pi c f hat c. Okay, so that's pretty straightforward, right? F is the Gaussian, then f is what they call an eigenfunction of the Fourier transform, right? It's something that it just gets scaled by 1 when you hit it with the transform. Okay, so now now we'll create the approximation of the identity from the Gaussian. Okay, so creating the concurrence. Okay, so for delta, let k sub delta be the Gaussian dilated by 1 over the square root of delta. So get x over the square root of delta, 1 over the square root of delta. So we take the Gaussian, we scale it, we dilate it by 1 over delta. So this, remember, dilation doesn't change the L1 norm. So we're not changing. All these guys have a norm of 1. Right, and they're positive, right? And they're positive because the Gaussian was positive, right? So we already know that the first 2 properties of the good kernel are satisfied. Okay. So this is e to the negative pi x squared over gamma, 1 over times 1 over gamma. Okay. So further, we also know, so we know that the integral of this, which is the same as the integral of its absolute value, since it's positive, is 1. Another thing that you notice is that if you take the Fourier transform of it, right? If you take the Fourier transform of it, well, it's the Fourier transform of a dilation, right? Fourier transform of a dilation turns into scaling, right? And so you get, right? It's dilation by 1 over the square root of gamma. Well, that was going to turn into scaling by the reciprocal of that. So we get the square root of gamma times c here, right? Now that is because the Fourier transform of the Gaussian is just the Gaussian. This is just a Gaussian evaluated there. So we get e to the negative pi gamma c squared. Okay, is that all right? Right. So this we're just using those properties from last time, right? So scaling turns into dilation by the reciprocal. Dilation by the reciprocal turns into scaling by the reciprocal. Okay. So now let's show what we wanted, that this thing actually is an approximation of identity. And this is actually pretty simple. So so our claim is that these functions, this thing is, as delta goes down to 0, an approximation of identity. Approximation of identity. And we just have to prove the third fact, but this is pretty straightforward. You just say, well, look, if we take the integral, I'm sorry. So I said it wrong over here. I was saying that the function needed to go uniformly to 0. It's rather that the integral outside of there needs to go to 0. So when I was talking about the approximation of the identity, I said the third property incorrectly. What we want to show is that that this outside of any, that for any eta, we want to show that this goes to 0 as delta goes to 0. Want to show that for any eta, that this thing goes to 0 as delta goes to 0. Okay, but this turns out to be pretty straightforward. Right? This thing is just, by definition, this is just 1 over delta e to the negative pi x squared over delta dx. Okay. But we can do a change of variables on that and see that that's the same thing as e to the negative pi y squared dy over over the outside of eta over root delta. Okay. So just do a change of variable on it, right? And then since e to the negative pi, since the Gaussian is rapidly decreasing, since this is rapidly decreasing, of course, as delta goes to 0, this is going to go to 0. Okay, so these guys, actually do form an approximation of the identity. Let me just make one side comment here. So remember this thing called the Dirac delta function, right? So it's this thing that when you integrate against it, you're integrating your function, and you have this Dirac delta function, which I'll denote by delta sub 0. Okay, and remember what this thing does. How it operates. It basically will give you the value of the function at 0. Right. So it's a weight of size 1 at a particular point. Right. It's really you can think of it as something like a measure, if you know this term. Okay. So suppose you take the Fourier transform of the Dirac delta function. What would that do? Well, that would be, you want to integrate the Dirac delta function, right, against e to the negative 2 pi I x c dx, right, from negative infinity to positive infinity, right? So what does that give you? That'll give you 1, right? Right, because it'll pick off the value of this function at 0, which is 1. So your ideal thing that you want to, and we saw earlier that convolving against the Dirac delta function would, if such a thing were allowed, convolving against the Dirac delta function would allow you to recover your function perfectly, and that is sort of embodied by this thing here, right? Because it's the thing which on the Fourier transform side it just recovers everything. Okay, but it doesn't exist, right? It's not, this thing isn't a function, right? But now think of the approximation of identity, right? These guys are all, these right? As delta goes to 0, then the Gaussian gets spread out like this, right? And as this goes to 0, then this function tends pointwise to to a spot. Sorry, I should say it on this side. No, on the other side, right? As this goes to 0, then this turns into 1, right? Pointwise, right? So that's on the Fourier transform side. You can see that the approximation of the identity is somehow approaching the thing that would be the identity. So that's how you want to think of approximation of the identity. Okay. Yeah, and on that side, it's turning into a spike. Yeah, a spike with the mass. It's a spike of mass 1 that becomes more and more concentrated at 0. Yes?
I was going to ask, because I think I've seen before, like, sharp changes in the regular domain are supposed to correspond to like a smoothing or flattening in the Fourier world. Why is that? Like, yeah. Or is this true?
Say it one more time.
Like, kind of like rapid movements in your f. Like if your function f is changing very rapidly, then its Fourier transform is smoother or flatter. Is this true? Is this the right way to think of this?
I don't think so, actually.
Okay.
No, I don't think
Okay.
so. It's rather,
Yeah.
yes.
But at least in the case of the Dirac delta function, it seems true. The Fourier transform is as smooth as it can be because it's constant, and the Dirac delta function is as spiky as it can be because it's infinity at one point and 0 everywhere else.
Okay, so then I guess my question is how should we be thinking of, like, what does the Fourier transform represents some form of like frequency decomposition, right? So how should we be thinking of it then?
So
Yeah.
So it is okay. So so it's okay. Maybe what you say is true, and I'm just thinking about something. I think I may be thinking about something else. But normally, I think the way one thinks about it is that, when you multiply, multiplication by polynomials on this side turns into differentiability on the other side.
Yes.
Right? So it's rather like the decay of the function here turns into smoothness over there. Right? Like if your function decays quickly enough on this on the function side, that should correspond to smoothness, differentiability on the other side. Right?
Okay.
But
Okay.
maybe, I mean, it's true what you're saying. I don't know. I don't know. Yes?
Is there a probability theoretic interpretation of what's happening here? Because the Fourier transform looks a bit like masses of frequencies everywhere, and then you're convolving against this thing that clearly has a probability theoretic interpretation.
That you're taking some sort of averaging of it? Yeah.
That somehow this is the expected value of the frequency or something, like given the right distribution or something.
Yeah, maybe. I don't know, but that sounds reasonable. Okay. Yeah, I mean, this is definitely, when you're taking the convolution, you're taking some sort of you're doing some sort of averaging. So.
And convolutions are also probability theoretic.
Yeah. Okay. 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 So definition. I don't know if we need to say this again, but just like for the functions that we had before, we define a convolution. Right, so convolution is just going to be f of x minus t, g of x dt. I'm gonna let you read this stuff yourself. That if f and g are in the Schwartz-class, then the convolution is still in the Schwartz-class, and the Fourier transform of the convolution is the product of the Fourier transforms. So just to show that, just to show, so I'm going to show now that just like before, the good kernels will allow you to recover your function. Given any f in the Schwartz-class, the limit of f convolved with the dilated Gaussians that we had before will converge back to your function uniformly. I realized that I had made a mistake in the lecture, so I'm going to fix part of it. So we had shown that the dilated Gaussian was an approximation of the identity, and we wanted to show the following corollary, that given any function in the Schwartz-class, then the limit of f convolved with this approximation of the identity actually does recover the function uniformly. So this is this uniformly converges to the original function, just like it should for just like it ought to. Okay. So So we want to show that given any. We want to show that given any epsilon, we can find a delta naught such that whenever delta is smaller than delta naught, we have that the distance between f convolved with k of x minus f of x is smaller than epsilon, and that this delta naught depends on epsilon, and it doesn't depend on x, right? Okay, so the proof goes like this. We say, well, look, the first thing we notice is that, so first observe that f is actually uniformly continuous on all of R. Okay, that any Schwartz function is going to be uniformly continuous on the entire real line, and that's actually easy to see because because you know that f decays rapidly, right? F decays rapidly, so you know that there's some interval negative n outside of which f is tiny, right? So you know that you can make given epsilon, there exists some interval, so that if we're outside of that interval, then the size of f of x is tiny, right? And so we don't have to worry about differences in f outside of that interval. And then inside negative n, and well, this f is continuous on this compact interval, so f is uniformly continuous. Right. So it's uniformly continuous inside here, and it doesn't change. Right? It doesn't change more than epsilon over 2 outside of here, and so we have that it's uniformly continuous on the entire line. Okay. So so now let's look at this thing, right? So if we consider now this, right? We consider this difference. Well, by definition, right? This is the integral of f of x minus t against k sub delta t dt minus f of x, right? Since k is a good kernel, we know that the integral of this is 1, and so we can play the same sliding in the constant trick, right? We know that that this, we can rewrite this f of x as this times the integral of k sub delta, right? Because that's 1, right? And that allows us to combine the two terms together. Right? So we get f of x minus t minus f of x times k delta t dt. Right? And so using the triangle inequality, we get this sort of thing, right? That this is less than or equal to the absolute value of this, and this is positive, so we don't need to put absolute values on it. Right? Okay, so we get this sort of thing, right? And remember, we want to show that, right? We want to show that so given epsilon greater than 0, we want to show that that there exists a delta naught such that if we're smaller than delta naught, then this thing is smaller than epsilon. Right? That this thing is smaller than epsilon. Okay. So the left hand, this term is this. Okay. Okay. So okay, so what we do is we say, well, look, we've got this integral over t, and these terms, the places where you evaluate them, differ by t. So, we can choose, as long as t is small enough, then these terms, we can control the size of this difference, right? So by uniform continuity, right, we know that if the size of t is smaller than some delta naught, then sorry, this is going the wrong way. If delta is smaller than delta naught, right? So as long as sorry, let me call this n, eta. Okay. By uniform continuity, as long as t is smaller than some eta, we know that this term f of x minus t minus f of x is going to be smaller than, say, epsilon, right? And that holds true for all x. That's the uniform continuity, right? Okay. So now we break this thing into two integrals, right? This is equal to the integral of this thing where t is smaller than eta, plus the integral over where t is greater than eta. Right? Now this thing, we know that this is going to be smaller. This is smaller than epsilon because t is smaller than eta. So this term is less than or equal to epsilon times the integral of k sub delta over this small integral. Right? but this is a positive integrand, and so let's just integrate over the whole real line. It'll just get bigger. The integral of that is 1, right? And so we got that this term is smaller than epsilon. Okay, and then on this side, well, we don't have control over this, but what we do have is that this is a good kernel, and so outside, away from any, away from the origin, we know that the limit as delta goes to 0 of this is 0. Right. Further, we know, f is a Schwartz function, so we know that it's bounded, and so this is smaller than twice the bound. Okay, so just choose delta naught, so that if delta is smaller than delta naught, then this thing is smaller than epsilon over 2a, right? So as long as delta is smaller than delta naught, then this whole term, right? This whole thing is going to be smaller than epsilon, right? And so we get that, we get what we wanted. We wanted to show there's a delta naught such that delta is smaller than that, then this difference is smaller than epsilon, and we get that it's smaller than 2 epsilon, which is fine. Okay. Okay. So right. Okay. And then the last thing that I showed was the multiplication formula, which we're going to need to get the Fourier inversion. So remember, our goal is to get the Fourier inversion, right? Namely that for S in the Schwartz-class, you can recover the function by taking the integral of the integral of the Fourier transform against the appropriate character. Right. So you take the the inner product of this against the right character. Okay. And so what will be useful in getting that will be the multiplication formula. So this is it. Right. Multiplication formula says that if you have two functions, then the integral of one function against the Fourier transform of the other is the same thing as integrating the Fourier transform of the first function against the function, the other function. That is, you can pass the Fourier transform from one factor to the other factor. Okay, and the proof of this is actually not that it's just an application of Fubini's theorem, right? So so here is the appropriate version of Fubini's theorem that we're going to invoke. So if f is a continuous function on R2, satisfying this decay condition, which is sort of like moderate decay in each variable, so 1 over x squared, 1 over y squared, then you can change the order of integration. So if you're integrating dx dy, you can change that to dy dx. And so the proof of this fact is just an application of Fubini's theorem. So it's not the most exciting thing. You say, well, look, this thing on the left, fg hat, I'm going to write as f of x, g hat of x, right? So g hat of x is the integral of gy e to the negative 2 pi I xy dy. Right. So by Fubini's theorem, we can change the order of integration. This turns into dx dy. The y pulls out of there, and we get gy f of x e to the negative 2 pi I y times x dx. Well, that's the Fourier transform. That's the Fourier transform of f evaluated at y. Right? The thing in the parentheses is the Fourier transform of f evaluated at y. So we get this, which is exactly what we wanted. Right? We've transferred the Fourier transform from G over to f. Okay. And so that is going to be that plus the approximation of the identity is going to be what gives us the Fourier inversion formula. Okay. Sorry, I had to redo that.